So, good evening. Is it audible clearly? So, are you able to solve the problem whatever I have given on the other day? No? Anybody? At least one person? No. Okay. So, let me solve that. So, there is no difficulty in it. That is simplifying the complex numbers. That's the only difficulty in that. So, note down this problem. So, that is when a pair of equal and opposite rectilinear vertices equal and opposite rectilinear vertices are situated in a long circular cylinder at equal distance from its axis. So that the path of each vertex is given by the equation r square sin square theta minus b square into r square minus a square being measured from the line through the center perpendicular to the join of the vertices. The join of the vertices. So, this is the problem statement. So, B is a random constant. It's just a constant. See this? So, why you are thinking of leaving this particular topic? See this. So, this is one of the very important topic. So, earlier actually the people used to follow the strategy of leaving this particular topic, and then actually so they can ignore simply. Why? Because this can be used as choice earlier, but not it is the same case now. So, the questions from this fluid dynamics and mechanics, many people are leaving this as choice. That's why UPSC started giving this particular chapter. So, into multiple questions it is separated. So, you cannot leave that as choice. Got it or not? So, that is one important thing what you need to understand. Another thing, one more important thing what you need to understand about UPSC is you cannot take anything as choice. Why? Because, so one important aspect is if you answer for 100% marks, then only you will be able to score relatively better than others. If you are thinking of leaving the choice in the preparation itself, so that is for sure that actually you will not be able to qualify. So, you cannot leave any particular topic as choice as part of UPSC syllabus. Got it? So, try to prepare all the topics. So, I have given elaborate explanation on each and every aspect of fluid dynamics. Now, actually it has got utmost importance because the questions are distributed between two other questions. Clear now? Okay. And then if you notice, there is not much of difficulty in understanding the fluid dynamics. The difficulty lies in complex analysis. So identifying a real part and imaginary part, this is the only section what you need to be focusing here. So given a complex function, so are you not aware of identifying the real part and imaginary part? That's what it is going to test it, nothing more than that. All the questions that are related to fluid dynamics, especially UPSC giving, right? So that is, everything is related to complex analysis one. So either you take, so only two different topics actually most of the times the questions were asked. Those topics are two-dimensional and axisymmetric flow, and then the vortex flow. Both are actually completely related to complex analysis. So 80% of complex analysis and 20% of the fluid dynamics analysis. Yeah, you need to practice. Yeah. So you can check Rai Singhani or Shanti Swarup. Both are very good books, but Shanti Swarup actually, though I am following, there were a lot of mistakes in it. So there were mistakes, but the mistakes were corrected in Rai Singhania. And the questions actually, so if you think a little bit further, so he has given certain procedure in the textbooks, but in some of the problems actually whatever I have noticed, right? So I could able to find out some shortcuts. Got it? So you also just read through that and then you will be able to find out shortcuts in it. Got it? The other day I have given one shortcut. So that shortcut, that is velocity square, if you want to find out, you have to multiply dw by dz and dw bar by dz bar. And then the product of that will straight away give q square for us. But actually in the textbooks, most of the times what he tried solving is, so without simplifying this, so he tried separating real part and imaginary part, and then he separated the phi value, and then dou phi by dou x value he used to find out, or actually dou phi by dou r or dou psi by dou r he will be using to calculate it. That will be very, very complex because the functions that are going to be involved, so a very, very complex level of complex analysis. Clear? So now actually even this problem also, if you notice, there is one circular cylinder like this. So this is the circular cylinder and this is the axis of the cylinder, and then there is one plus k vertex at this particular point, and there is one minus k vertex at this particular point. And this is, so he said that actually the line joining the plus k and minus k vertex, so if you draw a perpendicular or the bisector there, it is making an angle of theta and it is making an angle of minus theta there. And then being this is a circular cylinder, the image system of the circular cylinder will be, you have to place one more vertex of opposite sign here minus k at distance of a square by r. So this value is r, till this point it is r. Similarly at this point, you have to put at a square by r, you have to keep plus k vertex at this particular point. And correspondingly, you have to place one more vertex at the origin of magnitude which is exactly same as this one. And because of this actually there is one more minus k here. Because of this there is one plus k here. Both will get cancelled out. And then here there are no vertices you need to put in because both are cancelled out. So whatever is left over for us is plus k here, minus k here, plus minus k here and plus k here. So he asked us to find out the path of the travel of any one of the vertex out of these two is given by this particular relation. That's what he asked us to prove. Got it? So that means we have to identify the streamlines of this particular fluid particle. So the streamlines of this fluid particle will be, you have to identify the complex potential at this particular point. So as I said earlier, the complex potential of this particular vertex is nothing but the complex potential of all the vertices except for this. So the complex potential of the vertex at P. So this is I call as P and this I call as Q and this is R and this is S. So this is Ik by 2 pi. Oh, sorry. So at P actually Ik by 2 pi times of, now because of this it will be minus log Z minus Z1 or ZQ and then plus log Z minus ZS minus log z minus zr. So these are the three different complex potential you need to be considering when you wanted to find out the path of this particular fluid particle there. So we are ignoring this one because we are trying to consider this vortex motion. So here, so I hope you understood this concept here. Vortices are nothing but the rotatory components of the fluid particles that are happening there. So this is how actually it is moving. But if there is a vortex here also, this will influence this vortex to move away from this location. So this is the path of the travel of the fluid particles that are here. So that means this vortex is rotating like this and it is trying to move from there. Got it or not? So like this actually it keeps on moves and goes. So this path actually he asked us to find out. Now further the complex potential will be this one. Now this location is nothing but the xy coordinates, you can put it in the polar form. That will be r e power I theta, location of this particular particle. And then the location of this will be, so here actually the length will be a square by r, where a is the radius of this particular circle. So a square by r e power I theta is the location of this. And similarly, a square by r e power minus I theta is the location of this one. And then r e power minus I theta is the location of this particular particle. Now, so here actually you can notice that ZQ is nothing but, so r e power minus I theta, and then Zs is nothing but r a square by r e power minus I theta, and Zr is a square by r times of e power I theta. So these are the locations what we are trying to consider. Now these values actually we have to put it in this equation. So ZQ, Zs and Zr, you replace it, and then you can identify the value of Z. Z is nothing but r e power I theta. So because this is the location actually for which actually we wanted to find out. So Z is equal to r e power I theta. So all these values actually you have to put it here and then separate the real and imaginary part, and then the imaginary part will become the stream function for us. We use negative when it is inside, no? So this negative, see this, here actually if there is a positive vertex here, the corresponding mirror image will be minus k here. And here, because there is a minus k here, the corresponding mirror image will be plus k here. Got it? So that's why this is the image system of the circular cylinder, I explained. Now, correspondingly the complex potential will be Ik by 2 pi times of log of Z minus Zk. So Ik by 2 pi, that k is negative for certain values. Now, for this particular one, at Q, we have a negative k. And then, here actually, at S actually we have a positive k. This is plus k. And here, it is again minus k. That's the reason actually I have considered. Is that better now? Is the audio better? So, now actually we have to simplify this. Now actually our ability is to simplify only this, once we from. Now this one, Ik by 2 pi times of, now here I will replace log of r e power I theta minus r e power minus I theta minus of plus log r e power I theta minus Zs. So Zs is a square by r e power minus I theta minus log r e power I theta Z R will be a square by r e power I theta. So here this you can replace minus log r minus a square by r times of e power I theta. Then here actually ik by 2 pi minus log, here r if you take out e power I theta minus e power minus I theta, I will divide with 2i and multiply with 2i so that I can make this as the sin theta. And then plus log so you can keep this as it is, r e power I theta minus a square by r e power minus I theta, and then minus log r minus a square by r times of e power I theta. Ik by 2 pi. So this I can replace minus log 2 r sin theta times of I plus log r into I theta can be replaced with cos theta plus I sin theta minus a square by r times of cos theta minus I sin theta. Log r minus a square by r times of cos theta plus I sin theta. So this is how actually you can separate it, the real part and imaginary part. Now from this actually, so if you take the log from this out of all these things, so here cos theta plus I sin theta, yeah, I think so. We need to simplify this. Yeah, I think so. You can keep it as it is. So here, if you take minus outside, minus ik by 2 pi, and then this will be log 2r sin theta times of I plus, so this will become minus log, so this is cos theta plus I sin theta here and cos theta minus I sin theta here. So r minus a square by r times of cos theta plus r minus plus a square by r times of sin theta times of I, and then plus log r minus a square by r times of cos theta plus I sin theta. So this is minus ik by 2 pi So here actually we can divide this into the real part and imaginary part. Now actually the modulus of this is this square plus this square, and then this is the e power I theta format. Actually you can write it. So note down till this point. I am going to erase it. Done? Okay. So the simplified form of it is so minus ik by, so we will write only the imaginary part. So imaginary part will be psi is equal to k by 2 pi times of log of r minus a square by r. So because at e power I theta factor is there, so e power I theta, in that the real part and imaginary part I comes out. So the real part will become imaginary because there is an I in front of it. And then plus log 2r sin theta minus 1 by 2 log r square plus a square by 4, sorry, a square by a power 4 by r square minus 2a square cos 2 theta. So this is how you are going to get it after the simplified format. Got it? So I hope you understood how we have got these numbers. So that is in the earlier step, whatever we have taken out, right? So those steps actually we have to be separating the real part and imaginary part. So there is a one standard methodology, that's what we are adopting in all the problems. That methodology is, suppose, so log of something we are getting, that is f of x plus I times of g of x. This is how you are going to get it. Now in this methodology what we are doing is, so the modulus r actually we are writing as f of x whole square plus g of x whole square whole power 1 by 2, and then so theta is equal to tan inverse of g of x by f of x. So this is the standard methodology what we are using. Now actually this we are writing as log of r e power I. So this is based on the Euler's expansion, or Euler's theorem. So here again log r plus log e power I theta we are putting in. Now here this is log r plus e power I theta c. So this will be I theta. So this entire thing can be written as log of f of x whole square plus g of x whole square whole power 1 by 2 plus I times of tan inverse of g of x by f of x. So this is how actually all the parts of the complex potential whatever we have written in this particular format is written in this format. Now in front of that there will be one ik by 2 pi. So there will be one ik by 2 pi. Now if I multiply this inside, then this will be ik by 2 pi times of log f of x whole square plus g of x whole square whole power 1 by 2 plus I into I will be minus k by 2 pi times of tan inverse of g of x by f of x. So this is the methodology we are adapting. Now this can be written as phi plus I psi. Now psi is nothing but this part. So from this psi you are writing as k by 2 pi times of log of f of x whole square plus g of x whole square under root. So this is what actually we are finding out in all the problems. This is a generic approach. So this is the same approach we are following in all the problems. Is this understood or not? Right? Everybody, any questions on this? In this generic approach only we are putting in. Now along with that, the other information what you have to be aware in case of complex analysis is, okay, so note down this point, this part. This is very important. So note down this part. Along with that, the other simple principles, e power I theta plus e power minus I theta by 2 can be written as cos theta, e power I theta minus e power minus I theta by 2i can be written as sin 2 theta, sorry, sin theta, and then cos n theta, e power I n theta is written as cos n theta plus I sin n theta. So only these principles are getting used in all the problems whatever we have used till now. Second, this part what you are saying, this is not inside the log. Is this the one, Keshav? So this is log, right? There is a log present here. Log of f of x whole square, g of x whole square, whole power 1 by 2. This is inside the log. Got it? So this is inside the log. This is outside the log. Because r e power I theta, we are separating as log r plus log of e power I theta. So log and e will cancel out. I theta will be left over. Top line, which line? This line. Right? So this line actually in the earlier, the complex potential equation that was simplified, so simplified in this particular format to bring into this particular format. We have 3 different complex potentials. Now actually we simplified those 3 complex potentials together to get it in this particular format. And this is only the after separation of the imaginary part actually we have straight away written this particular format. As I told you, this is how actually we are simplifying. Finally what you are picking up is this part. Got it? Understood? Summary? So that we have to simplify. Yeah. Okay. Or you want me to simplify that format also? So I think one step itself, it will occupy entire board. Okay, so let me simplify that also. So the complex potential what we solved is W1 is equal to IK, so minus IK by 2 pi log of Z minus, so log Z minus A square by R e power I theta minus here itself we can simplify one more step, that is log of R e power I theta minus A square by R times of e power I theta. This is one complex potential plus log of R e power I theta minus R e power minus I theta. R e power I theta minus R e power minus I theta. So this is complex potential because of this A square by R e power I theta, that is this point. So this is because of the complex potential, this part. And this complex potential log of R e power I theta minus R e power minus I theta, that is this part. So this is the complex potential is written in this particular format. Got it? So this is being plus. So this will be minus k, and this is minus k, and this will be the plus k. So that's why if you take minus k out, so log will be plus here and log will be plus here. And then the remaining complex potential is this one, and that is log of minus log r e power I theta minus a square by r times of e power minus I theta. So that is because of this one. Now all these three complex potentials together, it will give the complex potential at this particular point. This will decide how this particular vertex is moving from there. Got it? So this part you understood, everybody? Okay. Now actually we will simplify this further. So for this actually, this one, W1 is equal to, so Ik by 2 pi times of log of r minus a square by r times of e power I theta, you can write it this way. And then plus here actually log of r, if you take it out, e power I theta minus e power minus I theta by 2i into 2i, I will take it. Why I have done this way is, so this I can make as the sin theta, because e power I theta minus e power minus I theta by 2i, it will lead to the cos theta, so it will lead to sin theta. And then whatever is left over is here the other way. Now that is minus log of, so r cos theta plus I sin theta minus a square by r cos theta minus I sin theta. This is how you can write. Now this part anyway you have separated the real part and imaginary part, and this part you can write as r 2r sin theta times I. You can keep that as it is. Okay. So this part actually will simplify it. Just take only this particular part because actually it takes time to simplify. Now this is log of r cos theta minus a square by r cos theta plus I times of r sin theta plus a square by r sin theta. So this is how actually you can write it. Now this part and this part, now we will write this in the angle, and so I call this as angle phi, and then r value is nothing but the square of this. So capital R is equal to r cos theta minus a square by 2 times of cos theta whole square plus r sin theta plus a square by 2 times of sin theta whole square whole power 1 by 2. So this part will be the modulus part, and the angle part phi is equal to tan inverse of, so tan inverse of the imaginary part is r sin theta plus a square by 2 times of, a square by r times of sin theta divided by r cos theta minus a square by r times of cos theta. So this is the phi value. Now this entire thing can be written as, so log of r e power I phi. Is this understood? Is this understood or not? Right? Samrin, I hope you understood. Now this is how actually you will write it. Now this part you have got the real part and imaginary part, and this part you have got the real part and imaginary part. So note down till this point, then actually I am going to simplify this. Done? Note it down. Okay. So once you noted down this, Now I'll write the real part and imaginary parts here. I'll put it exactly in that particular format first. That is ik by 2 pi times of r minus a square by r log of e power I theta plus log of 2r sin theta into I, right? So into I can be written as, so you have the real part 0 and the imaginary part is coming out to be 2r sin theta. So imaginary part is there and the real part 0. So tan inverse of y by x. So y by x is in the actual x is equal to 0. That means e power I pi by 2 you can write it. Got it? Right? So e power I pi by 2 you can write it. Now this is the real part and imaginary part. So here actually 0 plus I you can write as, so just I you can write as, this is cos pi by 2 plus I sin pi by 2. Because I is nothing but 0 is cos pi by 2, I is sin pi by 2. So this is e power I pi by 2. So e power I pi by 2 you can write this format. And this is what actually I have written in this format here. Now coming to this part, the simplified part, this is, so square root of, so a minus b whole square. This is, I'll just erase this. So this is log of r square cos square theta plus a power 4 by r square cos square theta minus 2r into a square by r into cos theta plus r square sin square theta plus a power 4 by r square sin square theta plus 2r into a square by 2, sorry, this is r, 2r into a square by r, this is cos square theta, and then this is sin square theta. Got it? Then here actually log of r square cos square sin square. So this is r square plus a power 4 by r square, so cos square plus sin square is equal to 1 again. Then here 2 a square, if you take it out, then it will be cos square theta minus sin square theta will be left over. So this is r square plus a power 4 by r square minus 2a square cos 2 theta, because this is cos 2 theta. So this is log of. Now you understood, submit. This is how actually we simplified it. So log of, so this is how you got. Now the imaginary part e power I phi will be there, where phi actually I have written in this particular format. Now here in this you have to separate the real part and imaginary part. Now here in this actually the modulus part, this is the angle part, and here also this is the modulus part, this is the angle part, this is the modulus part, and this is the angle part. Now you are multiplying with I here, that's why the modulus part will become the imaginary part for us in the overall function of phi. So this is nothing but phi plus I psi. So phi plus I psi, the psi part will be the modulus part, actually you have to separate it. That is, this is k by 2 pi if you take it out, I think minus k by 2 pi if you take it out, then this is log of r square minus a square by r, so log of r minus a square by r plus log of sin 2r sin theta minus log of this part, that is r square plus a power 4 by r square minus 2a square cos 2 theta. So this is what actually I have written in the previous step. Understood? Now, understood? Any questions on this summary? Oh, great. So once you get this one, this is nothing but the stream function equation. This will decide the flow direction. So if phi is equal to constant, this will be the streamlines equation. So as I told you, phi of r comma theta is the stream function. Stream function. And then phi equal to constant will always give the streamlines. Now I will be equating this to some constant. That constant what I take is minus k by 2 pi times of log b or log b. So this is how actually I take it, because k is a constant, phi is a constant, b is a constant. I can select my own constant, right? As I explained yesterday. In the previous class I have explained. So this constant you have got the flexibility to select anything. So this is constant, arbitrary constant. Inside log b or outside of log also it can be a constant. So but the constant number may be different, but it is a constant, a random constant. So if you introduce this way the constant, this k by 2 pi and this k by 2 pi you can cancel it out, and then log also you can simplify it, and then you can express in terms of b this entire functions, because log, so plus will get multiplied and minus will be divided. Got it? Understood or not? Got it? Okay. So now actually this is the simplified format, you have to write it. So for this actually there will be 1 by 2 coming out, because this one, the last part, there will be 1 by 2 coming out, because the square root of this actually is the actual modulus. So that's why you have to consider this 1 by 2, power 1 by 2 you have to consider it. That will come out. Got it? So the modulus part will be real part square plus imaginary part square under root. Okay. So once you got that, then the simplified format after cancelling the constant, you are going to get. So avoid the log from the simplification. So you will get r into r square minus e square, r square into r square minus e square sin square theta divided by r power 4 plus a power 4 minus 2a square r square cos 2 theta. And this will be b square. So the constant whatever we assumed is, that is some random constant, right? So this random constant what we have assumed is k by 4 pi times of log b square. So this is how, if you assume it, this k by 4 pi, and then log will cancel out on the other side and b square will be left over. So if you avoid the log, this is how you are going to get the function. Understood? Understood or not? Okay. So this part actually you can simplify it. Now this one, sin square theta can be written as 1 minus cos 2 theta by 2. You can write in that particular format. Then, so the simplified format, so this is r square into r square minus a square into 1 minus cos 2 theta by 2 is equal to b square times of r power 4 plus a power 4 minus 2a square r square cos 2 theta. So this 2 you can take it to this side. Now this will be r power 4 minus r square a square into 1 minus cos 2 theta. And then r power 4 minus r power 4 cos 2 theta minus r square a square plus r square a square cos 2 theta is equal to 2b square r power 4 plus 2b square a power 4 minus 4b square a square r square cos 2 theta. Right? And then you can simplify this. Only thing is actually you need to simplify this to put it in that particular format. Nothing more than that. Got it? So finally what you are going to get it is, that is 4a square b square r square sin square theta is equal to r square minus a square whole square into r square sin square theta minus b square. That's it. So this is what actually asked us to prove. So either you can replace cos 2 theta in terms of sin theta as 1 minus 2 sin square theta, or you can replace sin square theta in terms of cos 2 theta, and then you can simplify it, finally put it in this particular format. At the end you can replace with this cos 2 theta is equal to 1 minus 2 sin square theta. You are going to get this particular format. Understood? Is this understood, or do you have any questions on this? Yeah, this is a previous year question. Yeah. So only thing is the complexity involved is only in the simplification process. Only in the simplification process. And then in between actually the question, so we are assuming the random constant as, so rather than c, what we are identifying as k by 2 pi times of log c. So maybe sometimes b square, sometimes a square, or k by 4 pi. So only thing is k by something or k by something into log. So this actually you wanted to avoid, k by m into log. So that actually you wanted to avoid. Correspondingly you will be identifying the constant, so that you will be simplifying the entire equation without having any logarithms. Got it? Okay. So this is how actually you will be solving. Yeah. Okay, I will post it. Yeah. Fine. So these are all the problems. Mostly actually I have covered in the classes all the previous year problems. Most of the things are actually only the previous year problems, whatever I have solved in the class. Right? So these models are sufficient enough. You focus only on the two-dimensional and vertex flow. This is sufficient enough, along with the basic fundamentals whatever I have covered in the class. Right? So that is sufficient enough. And then, so today actually I am going to end this vertex flow, and there is only one, that is Navier-Stokes equation solution will be there. So that is actually very rarely, actually I don't think even asked any time till now. Very rarely it is going to be asked, Navier-Stokes equation solution, which I am going to take it up in the next class. Maybe 1 or 2 classes I will finish that Navier-Stokes equation. With that we are done with this fluid dynamics.